All right, let's try that again. Can you hear me okay? All right, let's see if that sounds a bit better.
I think you muted the actual Yeti mic or something.
Okay.
Sounds great though.
All right, now we got good audio quality and everything's going fine. And let me just make sure that we don't got anything else. Awesome. Glad to hear that you guys can hear me on the stream. So don't forget, I have John checking the comments for me, making sure if you guys have questions, he'll let me know. In the meantime, let's go ahead and get started with the lesson. So we're going to be working out of O2 MNIST today, along with stochastic gradient descent. And along with this lesson, I had a few requests, so we're going to look at deployment options and what that winds up looking like. We're still going to use Starlette, which is what Render was built on, even though you don't necessarily have to use Render anymore. The code base is still there for you to use on any platform. And we're also going to look at how do you explore the source code. And when you're wondering how a function works or what it looks like, how do you navigate it? Because I know that was a big issue with fastai1 in terms of, well, how do I know what X does Y? The source code and everything is somewhat difficult to follow. So first we're going to start with the image classification from scratch. So this is going to get a bit intense for the first half of the lecture. I'm not going to lie, because we are looking at, the PyTorch code. We're looking at what everything does, and there's a little bit of math. We're not going to know necessarily what the math does, more so how it works. So we're going to use the basics, vision, and callback library again. And we're going to use a dataset called MNIST. For those who don't know, MNIST is a dataset where it's handwritten numbers. It's 2 channels, so it's black and white, and there's 0 to 9. So let's go through and work with the data. Today we're going to use the lowest level API possible. So this is the data source, and we're going to look at how we go about using any input we want in the low level API. The first thing we need is file names, because the data source, which is what we're going to be using, runs off of a list of file names. So we'll use get image file and get a list of every single one of our numbers. And you can see it's set up to where we have our class and then the image itself. From here, we will be creating what's called a PIL image black white. So this creates a PIL image for us from a file name. And the .create method is when you pass in whatever you want before it gets sent to the model, pre-processing is done on this create method. When we explore the source code and you look at it, most any data sources, PIL image black white, PIL image, any of the tabular, any of the NLP, all have this .create method for the X's and the Y's. And so get very familiar with how that API looks, and you'll understand how to go about custom implementations for various inputs. Now, however, this is still an image, so we can call a dot show and see that we have a 9 here. Next, we'll use grandparent splitter, which we briefly mentioned last week. It'll make use of a train and validation folder. So we're going to pass in a training set name, which in our case will be training, and a validation set, which is testing. And what this will do is create an instance of an object that is set to split items. So it itself hasn't split anything yet. So let's pass in our file names. If we call splits here, pass in our items, and in reality, you should probably call this a little different than splits. Now we can see that we have our training set here at splits 0, and our validation set here at splits 1. What do we do now? Well, now we can make a data source. Data source is expecting the items that we want to use, some transforms, and the splits we mentioned above. Now, transforms, but what do those mean? What are those transforms? We're not talking about like cropping, resizing, and things like that. Instead, we're talking about how do we want our inputs to come in and how do we expect our y's to be formed. So when we go about making our transforms, I'll zoom in a little bit for you guys here. We have basically a list of 2 to 3 lists in itself as transforms, and that's depending on how many inputs you have. So what we're saying here is when we grab our x's, we're going to use PIL image black white dot create, what we used earlier to open our file name. And whenever we're dealing with our y's, we want to use the parent label, which is the folder, along with categorize, which says that I want to make everything into categories for us to classify with. And then finally, we pass in the splits that we made earlier, which goes by indexes and not actually by file names. Now, after you make this data source, we can look at a few instances in them by calling a method called showAt, where we will pass in the data source, whether we want the train or validation, and some index we want to look at. So I could say index 7 here. And you can see we have this 9 that kind of looks like a stick figure almost, probably a little harder to classify. And here we have, it's a PIL image with a label of 9 in this case. Now everything else from here we have to define by hand. Last week we saw that we just passed in, random resized crop and normalized, and we're good to go. Under the surface, there's a lot more that's happening because somewhere in that pipeline, everything's converted to a tensor, and then we get to apply all our transforms and pass it into a model. So here, we're going to define that. There's a transform called toTensor that does exactly what you would expect. And whenever we define these transforms, you read them left to right. Yes?
Someone's asking, are the transforms basically custom blocks?
Not quite. The question was, are transforms custom blocks? No. So the transforms still operate in the same way that they did in fastai2 to a certain extent. We can go look at that in the source code later. But instead, think of the transforms kind of like a pipeline. So here we have, toTensor, crop pad, and random crop. What's going to happen is the moment we get the image, it's going to be converted to a tensor, and then cropped and then padded to 34 by 34. And then we're going to randomly crop it again at 28 by 28. Now, remember last week I talked about the difference between item transforms and GPU transforms, or batch transforms. This is an instance of this. Anything that we have to do with modifying our inputs to get it ready to go into a batch, we need to do in the item transforms, which is what we have right here. Now, once we've gone through this, we can then do our batch transforms, which we can call CUDA to enable GPU usage, convert the integer tensors to float tensors to make them a little faster, and then normalize. Now here we're not doing normalize from stats because this is just our data set. And now we can data bunch our data source. And you'll notice that we don't have batch transforms and item transforms anymore. We have after item and after batch. So what that tells me is every time that I want to get an item, apply X transforms, and every time I grab a batch, grab the batch transforms. You can further make this more advanced. So let's try data source.databunch. And you can see just what all we can use. So these are all the options at your disposal. And you can see that we have like before iteration, after item, before batch, after batch. These are all different places that you can apply different transforms depending on how advanced you wind up getting. Now, it's not saying that's not happening. They're just occurring underneath the surface thanks to how we defined our inputs and how we defined our labels along with our splits. Does that help answer your question? We'll see. So from here, we have our standard data bunch. And so we can do a show batch, and it's all ready for our learner. Now, we need to know what our model will be expecting, what our input's going to be. We can do this by calling a batch, and we'll just call it XB and YB, and look at their shapes. Now, the shape tells us what size the tensor itself is. So if we look at So if we look at just a batch of our items, our inputs, the XB, is a 128 by 1 by 28 by 28 tensor. Now, what the heck does that mean? So our input image, remember I said it's a single channel, it's black and white. This is our channel. So it's one channel, that's 28 by 28. And we have 128 of them in a batch. We can see that if we do databunch.bs for the batch size, 128. And then our output should be 128 different labels, which is exactly what we have here. If you're outputting images, it'll be 128 images, or what have you. It'll vary depending on what your model is expected to return to you. And if we call .c, this will tell us how many classes we have. In our case, it's 10, 0 through 9. So now let's go into the model. This is where things are going to get a little heavier, but just stay with me. If it doesn't make sense to you, just read the code and kind of understand what the code's somewhat doing, and you'll be okay. So these models that we mentioned last week are made up of layers, and each layer represents a matrix multiplication until we get to the very last one and have our final y. For this particular problem, we're going to use convolutional layers, batch normalization, an activation function, and a flattening layer. So you could call this a convolutional neural network, or a CNN, like we saw last week with CNN Learner. So let's start with convolutional layers. So these will be the first layer in our network, and I'm going to borrow Adit's analogy. So let's say we have a 5 by 5 by 1 convolutional layer. So pretend you're in a dark room, and somewhere on the wall in front of you is our image. The only way you can look at the image is with a flashlight. That covers, say, 5 feet by 5 feet, and we have 128 feet by 128 feet. So what our model is essentially doing is shining a flashlight in one area, taking a wild guess as to what's going on there. This is also called a filter, which in our terms for our model is going to be called a kernel size. And the region it's looking over is a receptive field. So this filter or weights or parameters tells us kind of what the model is going to be looking at and what features it's trying to discern from this 5 foot by 5 foot picture. Now, the depth is the equivalent to how many layers we have. So in our instance, it's a black and white image, so we have 1. In your standard color images like we saw last week, it's 3 channels, red, green, and blue. Now, once we begin moving along our picture, or convolving, it's multiplying the values with the original pixel value of the image. So think pixel-wise or element-wise multiplication. At the end, everything is summed up to an individual value, which represents just the top left of our image. And then we go through, repeat this for the entire thing, and we get a feature map that has roughly 700 or so different locations that wind up turning into a 28 by 28 array, our pixels. Now, that's a lot, and that's okay if you don't understand that. Just follow along and see if it starts to make sense. So let's define a convolutional layer. Now we're just going to borrow from PyTorch's neuralnet.conv2d, where we're going to pass in an input, the number of filters, our kernel size, or the flashlight, a stride, and some padding. Number of inputs is the depth of our filter, and number of filters is how many filters. And it has to always be divisible by the size of our image to a certain extent. So that's why some models can take in any arbitrary image size, whereas some models can't. Now let's move into batch norm. So as we send them through our model, as we send our input through the model, it's important to remember that everything in statistics is normalized. So we want to keep our data normalized as best as we can. It allows for improvements in training speed, along with allows each of the layers to learn independently. What that basically means is, let's say we just normalized at the beginning, then those normalized values would dictate how the rest of the layers are operating and how their operations form. And so they're all kind of connected to each other. Allowing them to be independent gives us individual layer-wise attention and detail that necessarily we wouldn't have seen if it was still connected to the other layer. So we're going to use what's called batch normalization. In our case, it's a 2D image, so we're going to use batch norm 2D and just pass in the number of filters that we declared that comes out of our convolutional layer. And then finally, those activation functions. So these help give our model a sense of nonlinearity. So we work with the weights that we mentioned earlier, along with a bias, and this all occurs through a process called backpropagation. We'll look at that a little bit with stochastic gradient descent. But basically, we'll pass an image all the way through our model and then backpropagate those weights and correct after the fact. So with activation functions, we can then sort of help condense the model to focus on values that it should be caring about. So let's take this on a very simple level. ReLU. It's been one of the default activation functions for quite a number of years, and it's very simple. If it's anything above 0, then we'll keep it. Those values are fine, and we'll roll with it. If it's below 0, then we just crop it off at 0. It doesn't get to go any further from there. It's just 0, and everything's positive. If you want to learn more about that, there's a practical guide to ReLU available here. It's a little Medium article that you guys are more than welcome to read. So let's define that. We're just going to make a quick ReLU function that grabs ReLU, and we'll say in place equals false. This allows it to show up whenever we call the model. The last thing we need to do is what's called flattening. So whenever we output all of these activations, as I mentioned before, our output in the convolutional layer is something like 784 by 784. Well, how do we get that to 10? That's through this flattening module. So if we look at what this does, we can check the source code by adding a question mark, flatten x to a single dimension at the end of a model, or a full rank 1 tensor. Rank 1 just means that it's a single value. Rank 2 means it's an x and a y, so think our one-dimensional image. And then a rank 3, you have 3 dimensions, and you can go up from there. We can only realistically visualize a 3-dimensional, but they can go up to n dimensions. Now let's make a model. So we're going to have a very simplistic one. It's going to have 5 convolutional layers. We're going to wrap it around in a neuralnet.sequential, which says run these particular layers in this sequential order. And we'll start at a convolution size of 1, go up to 32, and then finish off at our 10 classes. So you can see we'll start at 1, we'll go to 8, 8 to 16, 16 to 32, and then back down in a trend that follows convolutional layer, batch normalization, and then our activation function. Now, this is pure PyTorch code. We haven't touched FastAI's library at all. So this is just one example of how you can define your own PyTorch model and then toss it in. So we're going to use learner today. This is different than CNN learner. It allows for any model, any loss function, any metric, what have you. So what we need, no matter what, is a data bunch and some sort of architecture we want to use. And we also have to pass in our loss function. You don't have to pass in a metric, as sometimes they're not applicable. But no matter what, you need these first three. Otherwise, the defaults will take care of your optimization function, initialization, and everything else. Now, one neat little thing that was added to fastai2 was learn.summary, which means that we can look at the exact output shapes of our model and make sure everything lines up. So here you can see we have a 128 by 8 by 14 by 14. Then we go to a 16, 32, 10 by 1 tensor. And then finally we get a 128 by 10. And we can also see which parameters are in fact trainable. And you'll notice that we never train the activation function because they only serve one purpose: change our negatives to 0 and keep our positives. Along with this, we can see what optimizer was used, the loss function, any callbacks that were noted, along with what our total trainable parameters and non-trainable parameters are. So it's a useful little function before you start training to help discern if you have any size mismatch errors or something, which we'll look at kind of what that looks like when we visit the next section. So let's go ahead and find a learning rate and fit for a few epochs. So we'll go learning rate find and then fit for 3 cycles. And you'll notice that we can call a pretty high learning rate here. It's a very simple model that can, and it's a very simple problem. Let me make sure that we don't have anything. Is rank the same as dimension? Yes. Yeah, so their dimension and rank are pretty much the same. So you have a 2D, rank 2 tensor, and a rank 2, or in a 2-dimensional, well, John, check me on that. Rank 0 tensor. Does that exist? Rank 0 tensor. I believe, yes. From what I've seen just now, yes. So it is the same. Dimension is the same as your rank. If someone finds that different, please let me know and I'll make that adjustment. But we can fit for 3 epochs, and it really doesn't take us long to get almost 100% accuracy on this problem. That's due to this problem is a very simplistic problem that's great for initial baselines, just to make sure your model works before you go test it on something else. Now, that was a very messy model definition. We're repeating a lot of things, and it doesn't look that clean. So let's see if we can clean that up a little bit. We'll create a conv2 layer, which uses FastAI's conv layers. Now, another goal of this lesson is to slowly work our way up to what a ResNet is, so you'll start seeing a few things being added. Let's look at this conv layer here. If we call conv2 and say we have 1, 8, what do we get? Our convolutional 2D, our batch normalization, and our ReLU. So now we went from having to specifically say them every single time. Now we're using the fastai library a little bit because we have conv layer. And now we're down to about 5 lines of code. Awesome. Now, just to make sure we didn't change anything, double check that we get pretty much the same results, and they're about the same. So now we know that what the conv layer is really doing is we have a convolutional layer, batch normalization, and some activation function. Now let's start working our way up to a ResNet. So the ResNet architecture works by having 2 of those conv layers we defined earlier wrapped into one, and follows this sort of module pattern. So what's really going on here is this anytime that we start this anytime we call this class, run this. And then with our layers, we also need to have a forward, because anytime we pass it through the model, we're passing it forward. And so it'll pass whatever our input is into this function. Now these res blocks will do whatever our original input is, plus passing our input into those two layers. Now for those of you that are familiar with PyTorch, might be very confused right now, because what you're used to seeing is something like the following, where we call a super dot underscore underscore init underscore, something like that, and we're not doing that here. The reasoning is Jeremy has created a new module type where we get to skip all of that. You can have a 2-dimension, which is rank 1. This corresponds to the maximum number of, I'm not sure. Okay, you can have 2 dimensions, which is rank 1. This corresponds to the maximum number of, yes.
So someone said rank 0 tends to be a scalar, and someone said, I noticed that the training error is greater than validation error. Is this because the problem is so simple? Typically, I think this means we're overfitting, right?
Yes. So on the rank, yeah.
That training loss and validation loss.
Let's see what we have here. So rank 0 is a PyTorch scalar. Rank 1 is a single dimension tensor, and so on. Thank you, Srinvas. I hope I got your name right. And then Rainier says, I noticed that the training error is greater than the validation. Is this because the problem is so simple? Usually that means that we're overfitting, right? Yes, it does. Now this is such a simple problem, and so it's a very simple solution here. Now part of that could also be, what you want to look at is how your data set was defined. Rachel has an article, and I'll link it in the chat later today, after the lesson, about how to build a proper validation set. Usually you'll either, if it's Kaggle, have some predetermined validation set that you're trying to fit towards and do good on. Or a lot of times you'll just have to make your own. And so trying to figure out what exactly works or not is difficult. And sometimes overfitting is a good thing. So long as on your either validation or test set, it's getting the results that you want on unseen data, then it's okay to overfit sometimes and not worry about it as much. But generally, yes, you do want your training loss to be lower than your validation loss. So now we have this res block, right? And we figured out that Jeremy has this cool little module here, subclass, that allows us to get rid of some initializations. And what this is doing here is called a nested call, essentially. So we'll pass X into our first convolutional layer, which then gets passed into our second convolutional layer, which is finally summed together. So let's add this to each of our conv2 layers that we had in the last model. So everything is still exactly the same, except we're incrementally adding these things. Now what that winds up doing is we take our very simple model here and turn it into something like this. Very, very large model that escalated very quickly just because we added a few more convolutional layers. So let's try to make it simpler, because that model definition was pretty long. As we can kind of see, we have a convolutional layer before each res block, and they have the same number of filters. So let's just make that into a layer. So we'll call it a conv_res, have a sequential that first calls a conv2d and then a res block. Now that very, very long declaration beforehand is this very simple problem. And you'll notice that the last layer we don't call a conv_res because we don't need to adjust the activations or anything. We don't need to pass it through to a different size. We just want it to go from 16 down to 10, because that's what we declared as our model's done enough. Give me the last 10, or give me the 10 classes this particular image could be, and what their probabilities are. So now let's see how it performs. We'll go ahead and call learner again, and we'll fit for 1e neg 1. And lo and behold, after 3 epochs, 99.2%. We did a lot better than the 98 we were looking at. And now some of you might be thinking, well, that's just 1%. Well, think about it on the flip side, though. Let's say this is identifying cancer in an individual. That's another 1% less error that we had before, which is always good. So finally, because we are going to work on deployment, for those of you running the code at home, you can go ahead and change your learner's path to your home directory here and export your learner. Now what that actually does is if we go over to this little tab, it'll make your export.pkl show up over here, or your .pickle file. And you can right mouse click it and download. Now we're going to save that for later whenever we go into deployment, and you can try to play around with it. So that is the ResNet from basically the foundations. We'll open up to questions for a second. Any other questions either here or on the forum? All right, I think we're all good. So now let's go into stochastic gradient descent. So stochastic gradient descent is basically how we fit our models to the data. So all we're going to need is fastai2 basics for this one. We're not really going to be doing a whole lot. We're just going to fit a line to 100 points. So stochastic gradient descent is an optimization technique, or an optimizer, like how we have Atom. It's commonly used in neural networks, and we're going to make a very brief example with linear regression. Something that's not too hard that most of you guys should at least either know about or are somewhat familiar with. Yeah, so the filter sizes, think of them kind of like a flashlight. So you can see right here, if we have a filter size of, let's go to it. So we have a filter size of 1. We're saying that we're checking every 1 pixel through and through, 1 pixel at a time, looking at the information that's given there and running a matrix multiplication on that particular pixel and how well it fits to some class. Scan that for the rest of the image in a 1 by 1 by 1. So we're going to do, for instance, this first one 16 times. Go through, grab everything, sum all of that information together, and then output some output. And so our model goes from a 1 by 1 to an 8 by 8 to a 16 by 16 before finally a 32 by 32, and then shrinks back down at the end. Does that answer your question? All right, so let's get back to the linear regression. So we're going to make 100 points to use on our fake model. So we can use torch.ones, pass in the number that we want, along with some arbitrary size. So we're going to want a bunch of xy's. So let's generate 100 xy's that are 1 by 1. Now let's go ahead and randomize this in some distribution that we know we can fit between -1 and 1. So we can do this by calling uniform, and then we can check and make sure that we have something that kind of looks randomized on our x's, and that our size is a 100 by 2. So remember, a model can be any linear model, is just y equals mx plus b, where m, x, and b are the matrices. And here we have x. We're going to be looking for b and m. So let's go ahead and declare a tensor that is 3, and we'll say it's 3 and 2. So it's just one of these coordinates, and we'll have some random bias. So we'll go ahead and create a bias that is n, so it's 100 long, equal to how many data points we have in our data set. Now we can generate our y. So whenever we do matrix multiplication, we have our b here, we have our b, our x, and our m. So when we do matrix multiplication in Python, in PyTorch, it's denoted with an @ symbol. So for our case, it's y equals x at m plus b. Now, you know you've done it wrong if you get this size mismatch error, which I said earlier we'd go look at. This means that somewhere along the line, everything didn't line up, and so you're trying to pass something in that isn't the right size. Usually the ways about fixing that is, first, if you're just working off of someone else's code, check that your inputs line up and see how far into the model you can go. If not, check and see that you're doing your forwards to go through the right way. Another thing that you can do is, so let's say I was curious because I'm getting a size mismatch error on, we'll say this batch norm right here. Let's go ahead and make our learner and do a learn.summary. Running mean should contain 16 elements and not 17. Well, I don't know what that means. Where do I go from here? Well, all right, so I have a hint that it's somewhere along where we have 16 and 17 in our model. So looks between about here in my batch norm. What fastai has is a, well, okay, maybe it's not in this version yet. There it is. We have a debugger layer. Now what this will actually do is load your Python debugger. So we can look at what our, so we can step here, step goes forward, we can look at what our retval is. And we have this very, very large tensor. And so from here, if you're noticing that you have some sort of an issue, you can go ahead and modify your code and look at what all is going on inside the model itself. Now, when you're ready to leave, you just do quit. And now you're out of the debugger. Just remember before you run your model again to get rid of this debugger layer. So now we've looked at what size mismatch really is. Let's go ahead and plot the results. So we have all of this. We have all of our x and y's right here. Now, what our weight should do is minimize the distance between the points in our line, also known as make a line of best fit. In order to do that, we need some way to make sure that it's actually fitting how we want. This is our loss function. Today, we're going to use mean squared error. And what we do is we take the difference between pred and y, subtract them, square it, and then average it overall. So let's look at what that looks like in code. So y hat is our prediction, y is our ground truth. So we'll take our y hat minus y, square it, and then get the mean of all of those values. And whenever we want to run our model, we're trying to predict what m is in terms of how to fit it best. So let's say we have an a of 0.5 and 0.75. That's just our input. We'll make a prediction and calculate our error. So we'll do y pred equals x at a, and then calculate our error. Y pred versus y. And this is the same y that we had earlier, if we go back. Now, what exactly does that mean? Well, let's plot it. So this is all of our data right now. This is what our current line is. And you can see that it doesn't quite fit there. Well, what do? Well, now let's train and optimize our function. So what's our goal? Our goal is to minimize the loss function, in our case mean squared error, using gradient descent, where we start with some parameters and move towards finding some new parameters that do a little bit better and take some steps in the negative direction of our descent to make it fit a little bit better. So first, let's make a parameter. This is just a neural network.parameter with our a from earlier. And you can see required gradient. That means that we are dealing with the gradients as we're going down. Now let's create an update function where we check to see if a improved. If it did, then we'll go a little further and let the model explore. If not, then we're just not going to worry about it. And we'll also print out roughly every 10 iterations that we do just to see that everything is going okay. You can see there's nothing too drastic here. We'll get our prediction, calculate our loss, print our loss if it's every 10, go backwards through our model and adjust all of our weights. That is the backward pass that I mentioned earlier with MNIST. And then finally, we're going to call, now this torch.nograd sets everything to evaluation mode. We'll go ahead and call this sub, which is our sub subtracts some value that's our learning rate times our gradient. Because we always want a learning rate. And if we have too fast of a learning rate, then our model winds up breaking because it can never learn anything. This is where and why that's important. So anytime we're going through, we're doing our learning rate times our gradient. And then at the end of everything, we want to zero those gradients before going through and updating our weights again. So let's do a learning rate of 1e-1 and go ahead and train for 100 epochs. So you see we started at about 3 and got down to 0.0846 before we really stopped improving. And let's see how this new A compares. So we want to detach whenever we do our x at A in order to remove all the gradients because we don't want those here. We just want the evaluations. Let's take a look at how we did. So the green was our original and the orange is our new. All right, that's a lot better. We actually have a proper fit. And in order to kind of steal home what we're doing, let's go ahead and animate it. Now this will also work in Collaboratory. We're going to create a new animation from Matplot that takes our parameter and goes ahead and animates a line that we generated earlier every time we call update. So this will just create a basic figure for us to use in a scatter plot, create a new line for us to use, and then go ahead and close the plot. And this will be run on loop. Now let's go ahead and see what this looks like. So here's where we began. This was the green line, and here's all our points. We're fitting to the line as best as we can. Now ideally, we want to split up our data into a series of batches and then fit, instead of here where we kind of just loaded everything all at once and fit. Most of the time, this is due to memory issues. If we have too high a batch, then you're going to get a CUDA memory error, and you got to restart your instance. And if this was a classification problem, we would instead be using the cross-entropy loss that we had last time, where we penalize incorrect predictions and reward incorrect predictions along with unconfident predictions and reward the good predictions. This can also be called negative loss likelihood. And those, that is how our models work and how they train. So I'll open up for questions for a little bit. We can go ahead and take a 5-minute break, and then we'll come back and look at server deployment along with navigating the fastai source code. Awesome. All right, so let's go ahead and get back to it. So now that we went through the rough stuff, let's get to the fun stuff. So the next bit we're going to look at is deployment. So we're going to be specifically looking at deployment with the Starlette framework. Now, we're going to borrow the original render deployment based on fastai v3 and use it for our purposes for fastai2. Now I have a link to the fastai2 template. I just made it earlier. So it's fastai2 Starlette. You can find it in my repositories. And along with that includes the deployment guide, which is this notebook that we're going to be running off of. So if you don't want to come back to the course repo, it's all there for you. So what will this really be focusing on? We're mostly going to be looking at what does the server code look like when we're deploying, and where does it all need to fit in for most any type of data. So that's going to be NLP, images, and tabular in a variety of situations. Now, I understand the last two we haven't gotten to yet. That's okay. I'm hoping that after we get to them, you can come back here and work on deploying them, or go ahead and explore the fastai lessons for tabular and NLP and work from there. So what code are we changing in this repository exactly? So let's first look at what everything we have here is. So we have this requirements.txt, which stores all of the versions and the version control that we're going to be running our app on. So anytime that you've got some weird library that you want to use, go ahead and put it in here. Now, the code that we're going to be focusing on is inside of app and server. This is server.py. And for those that are unfamiliar with server code, this is going to look a little weird with all this async and app routes. That's okay. The important bits that you need to care about is when we exported our file earlier, remember how we downloaded it? So we need to be able to access that remotely. What you can do is upload it to your Google Drive, And I just have a very basic example, export PKL here. And you hit share. And if you go to advanced, you can change this to anyone with a link. And now what you can do is copy this link and paste it into the download. I'll include another useful tutorial guide for how to take your downloaded link and move it onto there. But basically what you're going to care about, I believe, if I remember correctly, is the ID, but this should also work fine if you just paste it in there. So along with that, you're going to want your classes, whatever they wind up being, for your user to get a response back with what classes you wound up predicting. Or if it's regression, you're going to adjust accordingly. Now let's go look at what we're going to care about. So first we're going to look at images. And you can have a few different types of inputs on your server. And you got to think about what your use case is. So are we expecting our users to input one image at a time? Are we expecting a URL? Or are we expecting them to drop a zip file for us to analyze a bunch of images at one time? So we're going to declare this getBytes function right now. It's okay that that doesn't make sense. You'll understand kind of why we're going to care about that a little later. So let's first look at an individual image upload. Basically, we're going to accept a request, and we're going to get some bytes off of our off of the file that's attached. Now, learn.predict is really nice because it'll accept some bytes that you pass in. So we're going to use the bytes.io or bytes.io library, pass in our image bytes, and get some prediction back. So 0 will pretty much give you what your predicted class is, or the overall statistics. You can play around with the output of learn.predict to figure out which your particular use case would do best with. Now let's look at a URL. So now instead, we're going to use that getBytes function and grab the URL that was passed in, and again, just pass it into learn.predict. And let's look at a zip file. Now, the zip file is where things get a little bit trickier because we want to do everything more efficiently than just simple learn.predict, because that'll use your CPU. Let's look at how you can either A, use your CPU, or B, use your GPU if you really want it. So what this function is really doing here, now for those of you that do security, you'll notice a very big flaw here, but it's by use case. So we're going to have our user upload a zip file. We'll create some directory called downloaded images, extract all of those into this folder, and then grab our images, load our learner, and use this test DL. Now, this is going to eventually be replaced with learn.debunch.testdl. We noticed some, actually Sylvan noticed a few issues with tabular to that regard, so expect that to change sometime in the near future. But in the current version of the library, this is how it works. You're going to pass in your learner's data bunch along with the image file names you wanted. And the reason for that is, someone just posted a good discussion on overfitting. Highly recommend you guys read that. So that way you understand when you're overfitting and underfitting well, because it's a pretty tricky process. But TestDL will go through and look at what our validation transforms are and prepare our images for basically for passing into our model. And it creates a data loader for us. Now these are unlabeled. I'm working on showing an example with labeled data. There's a few different ways of going about doing labeled test sets. We'll explore that next week when we look at cross-validation. But we're going to be able to call getPreds, pass in our data loader, and if we pass with decoded, we will get back the original class names. And so that's why we only care about this third predictions. So now we can remove that folder, write everything to a CSV document, and return that CSV document to your user. We can do somewhat similar if we are expecting a CSV with image URLs. So the only thing different here is instead of get image files, we're going to instead download images and then get our image files. And that's pretty much most of the instances that I could think of for vision that you're going to come across in a business perspective. I highly recommend, if you guys find something else that works, go ahead and talk about it on the forums, say how you're deploying things a little bit differently, and share with others, because that's half of what makes this community so great. So let's look at tabular now. So tabular is a bit different because most of the work is done by sending a very large data frame into your model for analysis. So let's recreate most of what we did, but load it into pandas. So we're going to get a file. We're going to then read the entire file into string IOs. And pandas can actually read this as a data frame. So we'll load our learner. If you want to use, yes?
Someone says, can we possibly use /adapt nbdev to go from dev notebooks to code?
Absolutely. That is lesson 6, I believe. It's the style transfer lesson. We're going to go do that. Now here, it's not necessarily as useful for this code because we're looking at a server base, and so we can't run we can't necessarily run a localized instance because we need more than just the server.py in order to get everything up and running. And so it doesn't work per se in a Jupyter environment as well. But we are going to have a lesson where we go through and explore notebook dev. And specifically, how do we, in the workforce, say I've declared some model that I wound up building, how do I store it away in a .py file without copying and pasting a lot of code, along with generating a data set for us without needing to go through and download X, Y, Z. So if you want to take a look at what that is and get a little bit ahead of the game, if you go to the course repository and look at O5 style transfer, and let's load it up here. You'll notice that we're automatically using notebook dev right away. So if you want to jump a little bit ahead, go right ahead and do that. I believe that all that should be running. There wasn't any breaking changes yet. So there you go. Now back to the tabular. So at the current moment, this is going to be changing a little bit. Sylvain is working on trying to figure out a better way to go about doing this. It's a little bulky for right now. I'll update with what that kind of looks like. There's if you follow the V2 tabular forum, which if you're doing tabular work, you probably are, you can see our discussion there and how we went about dealing with it. From here, if we want to, I also show how we can store those results into our repository, our file system, and send it back to the user. The only thing different is we need to adjust our JavaScript to actually accept a form that we pass in. And so that's what this will add onto the client.javascript. And then finally, text. In this case, because text models are very, very large, it's going to, we're just going to assume that you're going to do learn.predict and nothing more unless you have access to a GPU. So that's sort of something to help you get started with deployment a little bit. That's just what I've found. My Knowledge on deployment is very limited, so I tried coming up with stuff as best I could for you guys. I'm hoping that more of you seasoned practitioners and veterans can help out others in guides like working with Docker and working with AWS and setting things up. I know there's quite a few references on the forums for setting up, Docker and other instances, because I know that's a challenge. That's what my father is doing right now for one of his deployments. So the last thing we'll touch on is how we go about exploring the source code. So I'm coming back to MNIST for us to look at just what we're going to be looking at. So let's say we have CNN Learner, and I want to understand what all it's doing. So we looked at earlier, we can attach a double question mark and see kind of what the source code itself looks like, but that's a little bit hard to read. So let's go through and look at what file that is. That's in fastai2, vision, and learner.py. So if we go over to learner and do CNN Learner, there we go. So it builds a confident style learner with some configuration, loss function, and some pre-trained, and goes ahead and grabs CNN model and eventually calls learner. Now, okay, that's cool. Let's go through and look at what learner does. Or really, let's go look at it from a different perspective. fastai2 was built off of the notebook dev library that was mentioned earlier. And so what that means is every single time that you have a module, you have a notebook to go along with it. So in our case, we were running out of Vision Learner. So if we follow these notebooks, which is fastai2 NBS, you'll find Vision Learner to be 21. Now, anytime the library is being updated, the notebook is being updated along with it, and eventually so are the course examples that you have here. So this is all of the original course converted over to fastai2. So let's take a look at this Vision Learner notebook. And so this kind of operates as living documentation, because since they are notebooks, we can go run this in Colab, install the library, and follow along with them. So if we go down to create, if we go down to CNN Learner, we can see models built from an arch using a number of final activation inferred by data bunch by getC. It might be pre-trained, and the architecture could be cut and split, along with an example of how you use it. And so now we have documentation that's being built as the library is being developed. Let's look at a different example. So we had our PIL image black-white, right? And I want to learn more about what that actually is, because the entire library is built off of this sort of module. So we can see that it's in Vision Core. I'm not even going to go look at the source code because that doesn't necessarily tell me much. I'm going to go look at the Vision Core notebook. So let's look at what we're finding here. If we go ahead and explore, we can go find PIL image. Declared over here. We can see that it's built on PIL base that has a create method and a show method. Now, any of your base types are going to be following this sort of pattern, where you're going to have some method that creates and prepares it for converting it to a tensor. And we're going to have a show method that brings our transformed and tensored item into something viewable on matplot library. So if we go down to, say, segmentation masks, or even to tensor points, which is a better example, we can see that we pass in some list of points and maybe an image size. This is actually figured out when you pass something in, and returns a 1x2 set of tensors. And if we want to show it, it goes ahead and plots those points. And so you can go through and play around with all of the code that the library is using without really needing to understand how the very basic operations are, because you can walk yourself through it right there in front of you and see, oh, all right, we're passing in an image. Let's take that image and add some points to it. I see what they're doing here. And anything that has hide or doesn't necessarily have the export is code that they're using to try and show and visualize what's going on. So I hope that that will help you guys in exploring the source code. It's really sit there, don't be afraid of it. It's not going to bite, it's not going to hurt you, I promise. And it's actually really helpful in understanding how the V2 library is really working under the surface, especially for those of you that are wanting to do custom implementations. And we're especially going to look at that week 6 whenever we deal with heat map key points. So I think that's about all the lesson that I have for you today. I think it was a little shorter than last week, but we also went over a lot of information. So go ahead and look over what we went through. Make sure that for those of you that are new to PyTorch, understanding what's going on there, play around with servers and deploying your model, and just have fun. So I will see you guys all next week.
We got one question.
We have one question. Yes, you can jump through the definitions in Visual Studio Code. Absolutely, and navigate it. I'm more of a fan of this oldish fashioned way of doing it by hand. The benefits of doing that is you get to go to, you wind up going to fastai2 and you can see the source code itself, but that doesn't jump you to the notebooks, I believe. Those of you that are more seasoned with Visual Studio Code can check me on this. I know they just added notebook support, but I'm more of going through and finding the notebook myself and looking through it rather than just looking at the .py file. So next week, I believe that we are going to be going over multi-label classification, and that's going to be the first sort of exciting and new technique, because we're going to go over multi-label, what happens whenever you want to tell your model, I don't know, along with we're going to look at cross-validation and how to do k-fold in the library. So thank you guys for watching. If there's any more questions, I will answer them before we go, but it does not seem like there are. So have a good night, and thank you for joining me.